All right, today we're tackling a classic coding puzzle, one that shows up in interviews all the time and can really trip people up. But what's cool is that hidden inside this chess problem is a super elegant technique for solving all sorts of complex problems. Okay, here's the game plan. We're going to start with the rules of the puzzle itself. Then we'll get into the recursive mindset you need to solve it, and we'll watch this whole backtracking dance play out. After that, we'll look at a really cool optimization to make it way faster, and then we'll zoom out and see why this one little puzzle is such a big deal. All right, first things first, let's get the board set up and really understand the challenge we're facing.
So here's the big question. And the goal here isn't just to find one way to do it. The real challenge is finding all the possible solutions.
Yeah, you can really think of this as a puzzle about constraints. We're trying to find this state of, royal harmony, where every queen on the board is totally safe from all the others. So here are the 3 rules of engagement. They're pretty simple, but they're strict. Basically, since a queen can attack horizontally, vertically, and diagonally, our solution has to make sure no 2 queens are staring each other down on any of those lines. Okay, so you might be thinking, why not just try every possible combination? Well, you could, but that brute force approach would be insanely slow. We need a smarter way to search for these solutions. So our high-level plan is pretty methodical, right? We're going to go column by column, placing 1 queen at a time, making sure each one is safe. Sounds simple enough, but what happens when our great plan runs into a problem? I mean, just imagine you get to, say, the 3rd column, and bam, every single square is already under attack. Are you just stuck? Do you have to throw the whole board away and start from scratch? And this, right here, is our secret weapon, backtracking. Honestly, the best way to think about it is like you're in a maze. When you hit a dead end, you don't just give up and teleport back to the start, right? No! You just walk back to the last place you made a choice and you try the other path. It's that simple. Okay, theory is one thing, but let's actually see this dance of trial and error in action. We're going to trace the algorithm's logic on a nice small 4x4 board so we can see every step. All right, here we go. Column 0. We'll try placing our first queen in row 1. Everything looks good so far, so let's move on to the next column. Now in column 1, looks like row 3 is a safe spot. No conflicts yet. So we keep going, moving on to column 2. And oops, we've hit a wall. In column 2, if you look, every single square is being attacked by one of our first 2 queens. This is a dead end. So, what do? It's time to backtrack. We literally undo our last move. We pick that queen up from column 1, and now we can explore different options from that previous step. But here's the thing. Turns out, there were no other safe spots in column 1. So we have to backtrack again. We go all the way back and undo our very first choice, taking the queen out of column 0. Okay, now we're back at the very beginning, in column 0. This time, we try the next available spot, which is row 2. And from here, the whole search process starts all over again. And by following this process, place a queen, check if it's safe, and backtrack when it's not, the algorithm eventually finds a complete, valid arrangement. Success! Okay, so we've got the logic down. But if you're in a coding interview, efficiency is everything. Checking for attacks by scanning the whole board over and over, it's just too slow. So let's look at a pro-level tip to speed this up, like a lot. So instead of scanning the board every single time we place a queen, we can make a classic trade-off. Use a little bit of extra memory to get a huge boost in speed. We'll use a few extra arrays that act like a lookup table, so we can check instantly if a row or a diagonal is already taken. Okay, so this is the really clever part. Check this out. For any diagonal that goes from the top left to the bottom right, the sum of the row plus the call is always the same number for every square on that line. So like square 0, 1 and square 1, 0 are on the same diagonal, and guess what? 0 plus 1 is 1, and 1 plus 0 is also 1. It's a unique ID, and there's a similar formula for the other diagonals. This trick lets us check for any diagonal attacks in what's called constant time. It's basically instant, a massive, massive speed up. So why did we just spend all this time on one little chess puzzle? Well, it's because backtracking isn't just for n-queens. It's one of the most fundamental tools you can have as a programmer for solving a whole class of really tough problems. And what's so cool is that the core logic we just walked through, That's the exact same logic that powers things like Sudoku solvers or algorithms that find a path through a maze. Anytime you have a problem where you need to explore a giant tree of possibilities to find the right answers, well, backtracking is your best friend. And really, this is the main takeaway. Backtracking isn't just randomly trying stuff, it's a disciplined way to explore. It's about making a choice, seeing where it takes you, and, this is the most important part, being smart enough to undo that choice and try something else when you hit a dead end. It's such a powerful mental model, not just for coding, but for any complex problem, really. So it leaves you with a question. What problem could you solve if you knew you could explore every path and you had the wisdom to know when to turn back? Thanks for joining us on The Explainer.